Hello everyone, today we're going to be learning lesson 1.6, Precision in Measurement. The learning goal for this lesson is to compare measurements for precision and perform calculations with the correct number of significant digits. So we're going to learn, so basically in science class, you may have heard about precision in significant digits, but if you haven't, you'll learn a lot more about that when you take chemistry in high school. So this is kind of an introduction to significant digits. But it's important when we are taking measurements to consider the precision, and when we have different calculations, to make sure that we are rounding in the correct way. So precision, looking at precision and significant digits, is all about how you round your answer to make sure that it reflects the accuracy of and precision of your measurement. So here's an example. You ask two friends for the time. Noah says that it is about 2:30. Mia says that it is about 2:28 and 19 seconds. Give the more precise measurement of the time. So as you might be able to see from this example, precision is kind of how specific you are. So it might be another term for specific. So obviously we would say that Mia's watch is a lot more specific because it tells you up to the seconds, where Noah's watch says it's about 2:30. But you're not exactly sure what the seconds are, or even what the minutes are. It doesn't even really tell you the minutes here. It just tells you every 15 minutes. So precision is the level of detail, how much detail your instrument can measure. So there are different scales that you can weigh things on, and some round, or even if you have a scale at home, some scales will tell you to the nearest tenth, while some scales might tell you to the nearest hundredth place, while some scales might just tell you to the nearest whole number. So here are some examples of how to tell which number is more precise. So 7 centimeters or 7.3 centimeters. So there are two different rules for precision. One is the place value, so the number with the greater or with the further place value. So if it has a further place value, or if it has a smaller unit, that's the other factor. It has a smaller unit. So these both have the same unit, but since 7.3 goes to a further place value of the 10th place, then this would be more precise. What about 5 yards and 16 feet? Well, they both go to the ones place, but feet is a smaller place value than yards. So this would be the more precise measurement, measuring something in feet. 1 pint or 16 ounces. So since ounces, once again, is a smaller unit than pint, 16 ounces would be the more precise answer. And then 14.5 inches versus 2 5/8 inches. Well, they both have a fraction and they're both in inches, but notice how the fraction here is, the denominator is 8. So that means that this fraction is being split up into smaller pieces, eighths, where this one is only split up into halves. So the 5/8 is a more precise, a more detailed answer than 1/2. So this would be the more precise answer. Okay, now let's talk about significant digits. To the nearest centimeter, the diameter of the United States quarter is 2 centimeters. So 1, 2 to the nearest centimeter, but it's not, it looks like it's a little bit more than 2 centimeters. So measured to the nearest millimeter, however, the diameter of the quarter is 24 millimeters. So that's another example of how you can be more precise with a smaller unit of measurement. The measurement, 24 millimeters, is more precise, given that it is a smaller unit of length. So a significant digit is the digits, the number of digits, where digits are just the numbers in a measurement that describes the precision of the measurement. So going back and looking at this example, part A, they both had the same units, but this had one digit in it and this had two significant digits in it. We'll talk about what it means to be a significant digit. Okay, this has one significant digit, this has two significant digits. So there are different rules for deciding if a digit is significant. The good part, the best part about these rules, you want to definitely want to write all of this down, is that anything that's not 0, so basically 1 through 9, is a significant digit. So you can count it no matter where it is in the number, if it's before the decimal or if it's after the decimal. So here you'd have 1, 2, 3, 4, 5. Number of significant digit, okay. This column, we can ignore this column. This is just saying which ones they are. Well, I'll just underline them. So 2, 8, 1, 3, and 9 are all significant. So that would be 5. However, it gets a little bit trickier when you have zeros. So sometimes zeros are significant, sometimes they aren't. We're going to skip actually, so this is rule 1. We're going to call this rule 2 because I think it's easier to look at first. So any zero that's between non-zeros is significant. So you see how these zeros are between 5 and 7. So those two zeros would count. And obviously 5 and 7 count because that's from rule number 1. So we have 4 significant digits for this problem. So any zero that's between other numbers that aren't 0. And this is the trickiest rule that people really can struggle with. So zeros that are to the right of both, so the right of both the last non-zero digit and the decimal point. So I'm going to have 2 examples here. So we're going to do also 70. So 0.0070 and then 70. So it says to the right. So that means if you're starting with 7 as being definitely a significant digit, then any zeros to the left does not get counted. So these zeros don't get counted as significant. This is just saying that these zeros don't really tell us anything about the measurement. They're just kind of placeholders for the 7. But however, this 0 does count. So why would this 0 count? Well, this is telling us that it's not just 0.007, that they actually did take the measurement into the tenths, hundred thousandths, millionths place. And it wasn't just 1 or 2, it was 0. So it was 0.0070 flat. So they took the measurement to the nearest millionth place to get the most precise answer that they could. So this 0 is actually significant because it tells us that this measurement was very, very precise. Whereas these zeros on the left don't count because they're just placeholders. So this would be, for this one, I'm going to draw an arrow here. This would have 2 significant digits. Let's take a look at 70 though. So the 7 counts, but this 0 doesn't count. Think about why. The reason why, because it says to the right of both the last non-zero digit and the decimal point. So is this to the right of the decimal point? You can imagine an imaginary decimal point here. So no, it's not to the right of a decimal point. So this 0 is actually just a placeholder 0. So this is just saying 70. So this would actually only have, sorry, I will get rid of this underline because we were saying underlines mean significant digits. 70 would just have 1 significant digit. Let's take a look at one other example for rule 3 is 70.0. So what this means is that when you took your measurement, you actually measured to the 10th place, and you determined that it was exactly 70 to the 10th place. So you were taking a precise measurement, and it was just exactly 70. So this 0, since it's to the right of the decimal point, then it does count. So basically, if you have any zeros that are in the tenths or hundredths or millionths place, those zeros count. This 0 would count because it's between these two significant digits. And then this 7 obviously would count because it's not 0. So there are 3 significant digits in that example. All right, so let's do some practice with determining the number of significant digits. Okay, so part A. So we have 290.01. So let's first underline the non-zero digits, 2, 9, and 1. Now, would these zeros count? Well, they are between 9 and 1, so they count as long as they're between 2 non-zero digits or 2 significant digits, then they count. So this would have 5 significant digits. Part B, 8 and 5 count. This 0 is not going to count because it's to the left of the 8. However, these two zeros count because they're to the right of the decimal and to the right of the 5. So there would be 4. Part C, the 4 counts. However, these 3 zeros do not count because they are not to the right of the decimal point, and there's nothing over here in the decimal point so that they could be in between 2 significant digits. So here there's just only 1. And then part D, the 5 counts. However, these zeros don't count because they are just placeholders for the 5. And they are to the left of the 5. They have to be to the right of the 5. And the right of the decimal. It gets a little bit tricky, I know, because even though these zeros are to the right of the right of the decimal, they're not to the right of the 5. So it has to be both of those two things. So this is only 1. And then I'm going to ask you how many are in both of these. So you should have answered now. So this would be, your answer should have been here 3. So these 2 zeros don't count because they're not to the right of the decimal point. The 8 and the 2 here count. This 0 does count because it's to the right of the decimal point and the right of the 2. These zeros count because they're in between 2 significant digits. So we have 1, 2, 3, 4, 5 in this case. So this is part 1 of this lesson. In the next video lesson you're going to watch next week is going to be about significant digits and calculations. So how to do calculations using significant digits. There are 2 different rules for addition, subtraction, and multiplication and division that will involve a whole nother lesson. So stay tuned.